Hello everyone. Today I'm going to show you how to model composite structures with 3D brick elements in ABAQUS. As we know that usually uh, plate and shell elements are the good choice for the modeling of composite laminates, but in the cases that we need some good reference solution, but there's no analytical solution. Uh, Maybe we can use ABAQUS 3D modeling to help us to obtain um, some detailed results to use. Okay, now I'm going to start the building procedure. Firstly, we go to the part module and we new a part. The the dimension I'm using is not very important. When you know how to do that, you can model whatever structures you want. And the problem I'm going to build will be a cantilever beam with 3 layers. To define the layers, we need to partition a face into 3 parts. Sorry. We need to define 2 lines. The 3 layers of equal thickness. Now we need to define the partition by sweeping these 2 edges. Now I can choose 2 edges at the same time. Okay, now we have the 3 layers. Next step, we need to define the material properties. We create new material by defining the engineering constants. Okay, and then we create new section property. It should be noted that here we choose a homogeneous option rather than the composite one. And then we assign the section property to the 3 cells. ABAQUS will automatically create new site as container for each cell we choose in the second layer, the third layer. And here we can find the commonly used layup manager, but in most of the cases is for plate and shell elements or solid elements, but that's another story. That's not real 3D modeling. We will discuss about that later, but today I just show you how to model um, a composite structure with commonly used 3D discretization method. And next step, we need to define the material orientation. And to do that, we need a local reference system. We create a new one by defining a rectangular Cartesian reference system. We choose the original point, a point on x, x, and another one on the x, y plane. Okay, we can check it here by clicking this. Now it's highlighted. That's our local reference system. Actually, it's the same with the global system we can see now. And then assign the material orientation by choosing this button. We choose the datum system. Okay, by default, ABAQUS will align the x, will align the fiber direction along the x direction. We can see here, and if we want to define some additional rotation, let's say the angles of the layups, 0, 90, minus 45, 45, we can choose the additional um, rotation, and the additional rotation in this case along the third direction of the element, or we should say along the third direction of the coordinate system we just choose, and we can define a 45 degree rotation for the first layer, and the stacking direction is along the element as a parametric direction 3. That means from the bottom surface to the top surface of it. And here we can see that this choice is only for the continuum shell only, but as I have mentioned, we later will discuss about it. And then we do the same for the second layer, and here we define, anyway, none means 0 rotation, and then for the third layer, let's say it's 90 degree. Okay, everything done here. And next step, we import this part to the assembly, and we can um, here check the layers we defined. Then we go to the step part, defining a very simple linear static analysis step, and here we cite the output variables we need. We have no contact. We accept other default setting. No interaction, we go to load. We define clamp boundary condition on one edge, and we can use a pressure load on the top surface of the structure. Okay, that's it. Basically, we're almost there, and now we need to mesh it. And let's say by default we have only one layer of solid elements in each layer, but that's not ideal because if we really want to plot some variables along some edges, or let's say through the thickness of the laminates, maybe in each layer we need at least maybe 3, 4, or 5 layers of solid elements. So we change that into maybe one, too many, and we can do this, and we choose to give 4 layers of elements each layer. Okay, this seems better. Four layers, exactly. And we cite the element type to be 3D stress, quadratic, reduce integration, C3D 20R accept. And something special is if we are using, let's say, linear elements with reduced integration. A special issue is for bonding problem, we need at least four layers of elements uh, through the thickness of the whole structure. So, but this won't be a problem for quadratic um, elements with reduced integration. But since we are uh, we want some good reference solution, we need some detailed description of the structural responses. So possibly the more elements, the better, but it has to be uh, computationally acceptable. Okay, now we have everything done. We go to the job part. Okay, I think we can override this. I hope it's not some big problem. It's going to be finished in maybe tens of seconds. Sorry for keep you waiting. Okay, it's done. Here we have the foam size stress, and what can be interesting is the distribution of the transverse stresses. Um, I should say that usually in the post-processing of ABAQUS, um, the stresses are plotted in the material uh, coordinate system, but we're not 100% sure that everything is is site according to our needs, and to make sure that we can change the reference system to plot the stresses. We go to results, options, and go to transformation, user defined. Um, uh, we should remember that when we were defining the material orientation, we assigned zero rotation to the second layer. And for the second layer, so the second layer can be used to plot our stresses. Okay, we can see that by changing the system, reference system, the results can also be changed. And another issue is if we want um, if we want the transverse stresses to be plotted along the edge through the thickness, what we can do is we can build a parse, this one, and then plot the stresses along this parse. So to do that, we need a card in the view. Let's see, we do it here. But you can change these coordinates according to your specific needs. And let's say we use this one. And then we go to the tools defining for defining parts, and we choose node list. and after. Choose the starting point and the ending point. Okay, seems to be correct. Okay, it's done. Let me go to the XY curve part and we choose parse. That's the parse we just chose. And we want to plot the curve in the undeformed shape. And by toggling this option, we can plot the results uh, on of the nodes between the starting and the ending point, and the x value should be z distance, and the variable to be plotted is sigma 1 3 as shown here. We can also change that by modifying here. Okay, now we choose 1 3 and plot. Let's see what do we have now. And this is some reasonable results. We know that theoretically the transverse shear stresses will be zero on the free surfaces, which is 0 on the bottom surface and 0, 2 on the top surface here. So that's what we got. And some friends may want to ask that, let's say in ABAQUS, when you are building a composite layup, uh, with the layup manager, you can visualize the structural laying up scheme. But for brick elements, we can't do that in the same way. But what we can do is we can plot the material orientation here in the post-processing part. Okay, now let's have a try. Okay, now we can see um, the three the the arrows with the three different colors shows us the different material axes. Let's say for the first layer we have 45 degree, for second layer 0, and the third layer 90 degree. This is also very useful for us to validate our results. And okay, basically that's it. If you have some problem, you can and questions, you can message me or send me an email. I will put my email address in the in the information part. Okay, thank you for watching this video.